Hello, Mr. Price here, and this is the 6th question on the June 2006 Mechanics 2 paper. This one is on angular speed and circular motion. Okay, let's take a look. It initially looks quite complicated, but once we break it down, it shouldn't be too bad. So our diagram speaks 1,000 words really here. I don't think there's anything hidden on here, but the key bits is we want to know is this a smooth plane? And I think we should find that it is a smooth plane. Smooth horizontal plane, and it hangs in equilibrium, also quite important. Okay, and we want to find the tension in the string and the angular speed. Okay, this is the same string, so the tension is going to be the same as an internal force. This is going to be quite useful for us. Okay, now let's model our two particles here. So, like with all circular motion questions, we want to see the force diagrams of the particle, or particles in this case. So, here is particle Q. It's on a table, so there's going to be a reaction force, and it has a weight of 0.3 g. And there is a tension in the string here. Okay, and this is the one that's spinning around. Okay, so that spin is caused by the tension in the string. So because this is spinning, there's an acceleration towards the centre of the circle. Okay, so there's an acceleration there. Okay, now for particle P, we know its weight is 0.5 g, and there's a tension in the string, and this hangs in equilibrium. So, working out the tension in the string here isn't too difficult. Resolve forces upwards. We get T equals 0.5 g. So the tension in the string is 4.9 newtons. Okay, that's the first bit for I. It also wants the angular velocity. So, in order for us to do that, we know there's an equation that links angular velocity to the acceleration. So now that we know T, we can resolve horizontally to find the acceleration here. So, resolving particle Q horizontally, the tension is equal to ma, because there's no other force horizontally. Another tension is 4.9, so 4.9 equals 0.3a. So the acceleration here is 16.3 recurring meters per second. Okay, but we want the angular velocity, so we know that a is equal to omega squared r, and we know the radius of our circle is 0.2 meters, so 16.3 recurring equals omega squared lots of 0.2. So omega, or the angular velocity, is 9.04 radians per second. And that is part I done. Let's look at part 2. So, it complicates it now a little bit more. So, our particle Q on the plane is now fixed to the point 0.2 meters from the hole, and now particle P is rotating in a horizontal circle of radius 0.2 meters. Okay, so don't really want to draw on this, but if this radius is 0.2 and this radius is 0.2, then at this point position here, they're going to be vertically below each other. Okay, and now I want to find the new tension in the string. So, for part 2, we're going to need some new force diagrams. So particle Q still has a reaction force, still has its weight, 0.3 g, and there's still a tension in the string. Okay, but this one is not accelerating. Okay, but it is fixed in position, so there'll be some kind of fixing force here. But we don't really care too much about that. Okay, and then particle P. We have our force. We have our particle here. It's still 0.5 g, but now the tension is at an angle. And we're going to rather importantly need that angle. Okay, so I'm going to draw this kind of triangle here to see if I can work out one of these angles. So, this is particle Q. This is the hole. And this is particle P that's vertically below it. Okay, we know this is 0.2. And this is where it looks like we're stuck. But if we look again carefully at the question, at the very start here, we're told the length of the whole string is 1 meter. So this is 0.2, then this bit must be 0.8. So now we have enough information to get this angle here, alpha. So using sine alpha equals the opposite over the hypotenuse. We should find that our angle here using inverse sine is 14.478. Okay, so here we have 14.478 degrees. So now we can resolve just like we did for part I, vertically to find the tension. So T cosine 14.478 is equal to 0.5 g. So the tension in the string is 5.06 newtons. And that is part 2 done. And now finally for part 3, we want to calculate the speed of P, the tangential speed. So at this point there's not really too much left to do. So for particle P is accelerating like so. So resolving in a direction of acceleration, we have 5.06 sine 14.478 equals ma. We know the mass, so the acceleration here for this particle is 2.53 meters per second. So earlier we knew that A equals omega squared r, and we know that the tangential velocity varies as you go away from the radius linearly. There's a linear relationship there. So V equals omega r. So that means we know that omega equals V over r. So we can substitute this into here. So A equals V squared over r. And now we can work out the velocity from here. It's quite simply 0.711 metres per second. And that is question 6 finished.